A warm welcome to the 19th session of the second module in the course Signals and Systems. We have seen in the previous session how we can decompose a periodic waveform into its complex exponential components as opposed to sinusoidal components. There we saw how we could go from the sinusoidal components to the complex exponential components. Now we shall do the converse. How do we go from the complex exponential components to the sinusoidal components? So, one thing is to be noted. Let me in fact make that point clear by reviewing what we did towards the end of the previous session. You will recall that we had already identified if xt is periodic, period t. You will notice I am writing this again and again just to put the context in clarity, and we have a sinusoidal decomposition. So, as I said, we will separate k equal to 1 to infinity and k equal to 0. You know, you do not really need to write a0 cos phi 0, though that is of course a consequence of the expression. We can simply call it a0. You can always modify phi 0 accordingly, you see. So, this can now be decomposed. So, you have summation k going from 1 to infinity, ak by 2 e raised to the power j phi k e raised to the power j 2 pi by t kt plus same thing, but with a conjugation, and then plus a0. Now, notice, as I said, that this is equal to Ck for k positive, and this is equal to Ck for k negative. And notice that for k positive and k negative, the corresponding k positive and k negative, you have complex conjugates. Let us look at it. So, if you look at this, take the corresponding k here and here. If you take the corresponding k, you have complex conjugates there. So, we will write this down formally. Ck is equal to C minus k complex conjugate for k going from 1 towards infinity. And of course, C0 is, it is real, and in fact it is expected to be whatever, it is essentially an average, and that is equal to A0 actually. So, this is true if xt is real. And that is what we have assumed when we made a sinusoidal decomposition, as assumed. But this is where we want to be a little more general now. We do not want to confine ourselves to real waveforms, in which case this can be violated. So, Ck may not be equal to C of minus k complex conjugate if xt is not real. Let us write that down clearly. So, will be violated if xt is not real, complex and not real. You see, take the very trivial example of one single complex exponential. If you have one single complex exponential rotating with a period of t, you need to take only one term in this complex exponential expansion corresponding to that particular angular frequency of rotation, and all other terms are absent. That is a very simple example of a complex signal which does not have a sinusoidal decomposition. Now, how do we go from the complex exponential decomposition back to the sinusoidal decomposition? So, let us look at that. Complex exponential decomposition to the sinusoidal decomposition for real xt. Very easy. Write xt, you have assumed it to be real of course, in the form summation k going from 1 to infinity Ck e raised to the power j 2 pi by t, same summation but with minus k instead of k, and C0, and C0 has to be real as average is real. You know how to calculate C0. C0 is essentially 1 by t integrate xt dt over an interval of t. Now, we know what to expect for Ck and C minus k. So, you know that these are complex conjugates. and therefore, let us take them together. So, x t is C 0 plus summation k going from 1 to infinity C k e raised to the power j 2 pi by t k t plus C k complex conjugate and the complex conjugate of that rotating phasor 2. So, you will notice that this is essentially the complex conjugate of the whole term. So, we have a sum of two complex conjugates. When you have a sum of two complex conjugates, it gives you essentially 2 times the real part of any one of them. So, let us write that down. Now, how do we write down the real part? So, real part is essentially the real part where you write Ck in polar form. Here you have written Ck in polar form, magnitude and angle, and that gives you mod Ck cos 2 pi by t kt plus phi k, where phi k is essentially the angle of Ck. So, overall what we have is x t is then C 0 plus summation k going from 1 to infinity 2 times mod Ck cos 2 pi by t, and here essentially we have a sinusoidal decomposition. So, essentially here A k is 2 mod C k and phi k is of course as it is. Now, once you have, so it is very clear, for a real signal you can go from the sinusoidal decomposition to the complex exponential decomposition, and you can go back from the complex exponential decomposition to the sinusoidal decomposition, very simple. So, I do not need to illustrate these separately, is that right? We have already taken a few examples. What I would encourage you to do as an exercise is to take the same examples, decompose them using the complex exponential decomposition by the formulae that we have written, and then go back to the sinusoidal decomposition and verify that they are the same, just to satisfy yourself. That would be a concern. Let me just take an example. So, what I am saying, for example, is you could take, for example, the square wave. So, exercise, decompose the square wave, let us take an asymmetric square wave for variety, and let us take only a part of the cycle to be present from 0 to t1 into its sinusoidal. So, this is a periodic. So, of course, this is x of t shown between 0 and t, but x of t plus t is equal to x of t for all t. Decompose it into its complex exponential components and its sinusoidal components. Go one from the other as discussed and verify. This is the exercise I would recommend you do to understand these two decompositions very well. Thank you. We will see more in the next.